In this video, we're going to talk about describing quantitative data in terms of measuring variability. One of three big ideas about measuring variability is range. I bet you've heard of range before. I bet you've calculated range before. So range is the distance between the minimum value and the maximum value in terms of your data distribution. So the range of a data set is a single number. So it's just a subtraction problem, really. Our very favorite piece of data here, right? The 20 games played by the 2016 U.S. women's soccer team. The highest number of goals scored in a single game was 10, at least in this sample, and the lowest is 1. So the range, 10 minus 1, is 9. The second big idea about measuring variability is something that we call standard deviation. So we're going to talk a lot more about standard deviation, but essentially this is what it is. So it measures the typical distance of the values in a distribution from the mean. And remember, the mean is the average. So algebraically, here's how you calculate standard deviation. It's also represented as S sub x. So the first thing that you do in your distribution, you find the mean, you add up all the values, divide by the number of values, there's your mean. You're going to calculate the deviation. So don't worry, we'll work through an example of this, so don't feel like you need to memorize all of these right now. So that second part, you take the deviation, which is the value, so that data point, you take that value, you subtract the mean. And then with all of those individual values, all of those deviations, you square each of them. You add up all of those squared values, you divide by n being the number of values that you have, you subtract 1 from that, so you divide by 1 less than the number of values you have, and then you take the square root. And that, my friends, is how you calculate standard deviation. So in terms of a formula, this big thing essentially boils down to that, where we take the square roots, essentially working backwards, right? Square root, the sum of these deviations, the square of all those deviations, divided by that n minus 1. So, as promised, here's that example. This example is called How Many Friends? 11 high school students were asked how many close, in quotation marks, close friends they have. Here are their responses in a dot plot. So thank you, whoever organized this data. It's in numerical order. So there are 11 values here, and they range from 1 close friend all the way up to 6 close friends. So let's calculate the standard deviation and interpret what on earth this means. So the first of those steps is to find the mean of the distribution. So let's do that. So when I add up all of those values here, I get 33, and there are 11 values, so 33 divided by 11 is a nice, crisp 3. So here's what we're going to do from there. We've got our mean, which is 3, and I'm going to combine these two steps here. So we're going to calculate the deviation. So what that means is we take each of these values, which I've set up in this chart, which helps me organize finding standard deviation in this way. So this list of numbers, we've got our mean. I'm going to take each of these values, so x sub I, and we're going to subtract the mean from it. So we're going to go 1 minus 3, 2 minus 3, etc., all the way down the list. And then this result we're going to square. So for example, with 1, we're going to subtract the mean from it, so 1 minus 3, that's negative 2, and when you square negative 2, we get 4. So I'm going to do it for the rest of these values and come back. So for each of the 2's, I get a negative 1. Square that, I get 3 positive 1s. For 3, 3 minus 3 is 0, so that's 4 zeros all squared. For 4, I get 1. 1 squared is 1. And then for 6, 6 minus 3, 3 squared is 9. So we have squared each of the deviations. So what I'm going to do is I'm going to add up all these values. So 4 plus 1 plus 1 plus 1, etc. down the list. And that sum is 18, adding up all those values. So now we have to take the final steps here. We're going to take the square root eventually. So we've got the square root of this ratio. So 18 divided by n minus 1. N, remember, is the number of terms. So we've got 11 of those. We take away 1, we've got 10. So 18 divided by 10, take the square root of that, and our standard deviation is approximately 1.34 close friends. And if we were going to interpret this value, we would say that the number of close friends that the students in this sample have typically vary by about 1.34 close friends from the mean of, on average, 3 close friends. So there's some other important properties of standard deviation, or S sub x, that I want to make sure that you know. So standard deviation is always greater than or equal to 0. You're not going to have a negative standard deviation. And with a special case, in my opinion, if your standard deviation is 0, that's when there's no variability at all in your data set. So all of the values are the same. Second property is that larger values of a standard deviation indicate greater variation from the mean of a distribution. So in this example, we're talking about the length of a PVC pipe based on the supplier. So this top one here has a standard deviation of about 0.68 millimeters, and this second supplier B has a standard deviation greater than 2. So this is a greater standard deviation, so that means it has greater variation from the mean, which should make sense. If your data is more spread out in layman's terms, then you're going to have a greater standard deviation from the mean, or the average. The third point here is that standard deviation is not a resistant measure of variability. What happens when we use squared deviations, that makes our standard deviation even more sensitive to extreme values from the mean. So if we take a look at our very favorite, possibly overused example of the 2016 U.S. women's soccer team and the goals that they scored. So taking into account all of the values, including these 2 outliers, the standard deviation is over 2.5 goals from the mean. But when we remove those 2 outliers of 9 and 10 goals scored in 2 different games, we find that our standard deviation from the mean of just this data drops down to 1.46 goals. And the last property that we're going to talk about, at least for this video, is that standard deviation measures variation about the mean. So it should only be used when the mean is chosen as the measure of center. Something that helps us avoid the impact of extreme values on our measure of variability, like standard deviation, is chunking up our data into what we call quartiles. So if you think about the word quart, and you might think 4, we do break things up into 4 different sections. So a quartile of a distribution divides the ordered data into 4 groups having roughly the same number of values. To find quartiles, you range the data from smallest to largest, and then you find the median. So we're starting with the median, which is also called the second quartile. It splits the data in half. So the first quartile is the median of that first half. So you split it in half again, there's your first quartile. Then to find the third quartile, you take the second half of the data and you split that in half, and there's your third quartile. And so when we want to measure the variability in the middle of the distribution, that's something that we call the IQR, or the Interquartile Range. So what we do is we take that Q3, or that third quartile value, and we subtract the first quartile, or the Q1 value, and there is our IQR. So let's put all that quartile knowledge to the test and work out an example. So this example, now pardon the gender binary here, but the example is called Boys in Their Shoes? ? So our problem is, how many pairs of shoes does a typical teenage boy own? To find out, 2 AP Stats students surveyed a random sample of 20 male identifying students from their large high school and recorded the number of pairs of shoes that each boy said that they owned. Here's the data. So here is the unordered list and a dot plot. So it looks to be that the smallest number of shoes reported is 4 pairs and the largest is 38 pairs. Now, let's do some work, find our quartiles, and then find the IQR, the interquartile range. First thing that we're going to want to do is sort the data values from smallest to largest, and then from there we will find the median, or the middle value. So I've written all of these numbers in order. I cross them off, as I always do, and then I know that there are 20 values here. So that means that I'm going to have to take the average of the 10th number in from the left and the 10th number in from the right. And so those two numbers are 8 and 10, and the number that comes smack dab in the middle of those, 8 plus 10, 18 divided by 2, that's 9, so our median is 9. And then from there, we can find our Q1, so that takes the first 10 numbers and we count 5 in there or count 5 in that way, and we find that our number in between there, so the median for the first half of the data, or our Q1, our first quartile, that's going to be between 6 and 7, and that's going to be 6.5. Going to do the same thing, finding the median on the second 10 data points, or number of shoes. So I count 5 in this way or 5 that way, and I find that the third quartile, or the median of the second half of the data, Q3, is between 11 and 12, so Q3 is 11.5. And in order to find the interquartile range, we subtract Q1 from Q3, so that's 11.5 minus our 6.5, and that means that our interquartile range is 5 pairs of shoes. What I'm about to do next is a total teacher move. Sorry, not sorry. But let's say you want to check the data and the numbers and all the things that you just found for that list of shoes. Your calculator can help you do that. So on your TI-83 or 84, you hit that stat button, you enter in your list, and then when you go to calculate, you can click one variable stats. So from that calc list, you'd pick one var, stats, var meaning variable, and it gives you a whole host of information. And here's a rundown of what all of these things really mean. First one up is x bar, that is our mean. Sigma x and sigma x squared, so that's the sum of all of the elements, you add them all up, and then the x squared is the sum of all the squares, so that's important in standard deviation. So next you get sx, and then this little whoop, x. Fun fact, that is the lowercase sigma in the Greek alphabet. But you can call it a whoop if you want. S of x is your sample standard deviation, and that little whoop, that little baby sigma x, is the population standard deviation. We covered sample and population in another video. N means the number of elements in that list. So for example, we had 20. Min x, the same as max x, or well, they're related, not the same. But min means minimum value, and max means maximum value. Q1 is your first quartile. Med is your median, and Q3 is your third quartile. So yeah, your calculator can do that for you. Again, sorry, not sorry. Also really wonderful and useful is identifying outliers with the 1.5 times your interquartile range rule. What that rule states is that if you observe an outlier, or if you're curious if you have an outlier falls more than 1.5 times the IQR, the interquartile range, above the Q3, or the third quartile, or below the first quartile. So if you have a low outlier, that is going to be less than the value of whatever your first quartile minus 1.5 times your IQR, and then on the opposite end, you've got high outliers. So that's going to be a greater value than your third quartile plus 1.5 times your IQR. So if you remember back a couple videos to the EPA surveying a sample of 25 model year 2018 Toyota 4Runners to test the highway fuel economy in MPGs. So we had this value over here, and we have this value over here. They look like outliers, and here's how we can mathematically figure it out. So we're going to test these two things. So a low outlier, the Q1 ends up being 22.2, and then 1.5 times your IQR is 1.5 times 0.04, so that's 21.6, and 21.5 is less than 21.6. So that value right there, that is a low outlier. And then on the other end of the spectrum, we think this 23.3 might be an outlier. Let's calculate it. So the Q3 here is 22.6, and then we add 1.5 times its IQR, which is still 0.4, and that ends up being 23.2. 23.3 is 0.1 bigger than 23.2, so that is a high outlier. You didn't really think that I was going to leave you hanging without doing an example together. Oh no, no way. Never leave you hanging. All right, let's take those 20 games and those goals scored by that 2016 U.S. women's soccer team, and let's identify any outliers. So what I'm going to do here is I've got all my numbers in a row. Thank you to whoever ordered those for me. I don't have to do that. So I'm going to find the median. I'm going to find Q1 and Q3 in order to find our IQR. So what I did is I found my median. I counted 10 this way or 10 that way, and the median's going to be 2 because half of 2 plus 2 is 2. And then so I cut the first half of our data in half, and that's going to give me Q1. That's split between 1 and 1, so Q1 is 1. I'm going to do the same thing for the second half of the data to find Q3, and when I do that, either count 5 that way or that way, I have a number in between 4 and 5, so Q3 is 4.5. So let's subtract 1 from 4.5 to find the IQR. 4.5 minus 1 is 3.5. Now let's test to see if we have any low outliers and high outliers. So for low outliers, I'm going to take Q1, which is 1, and then subtract 1.5 times our IQR, which is 3.5. So I have 1 minus 1.5 times 3.5. Using PEMDAS, multiply that first, get 5.25. 1 minus 5.25 is negative 4.25. So there is no value here that is lower than negative 4.25. So there's no low outliers. So let's do the same over here with addition for high outliers and see if we got any of those. Spoiler alert, I think we've established that we do, but let's mathematically prove this. So doing the algebra over here, 1.5 times 3.5, that's still 5.25, but I'm going to add my Q3 to that, and I get 9.75. Are there any goals that are greater than 9.75? There's one, 10. So 10 is my only outlier. Not 9, only 10. All right, I'm off to reread the book Outliers now, and that's going to do it for this video. Thanks for watching.